and take a few minutes while people are still getting settled to respond to a query. The discussion of the Hyperloop. I had mentioned the Hyperloop a couple of lectures ago, a couple of weeks ago, and someone called me on the carpet and said, you haven't explained your answer to why the Hyperloop isn't going to work. So let's take a look a few minutes while we're getting settled and everybody's coming back with their coffee. We'll just have a preliminary little talk about the Hyperloop. So this is, you can Google this, the Hyperloop, this idea of a giant postal tube for passengers to go from Los Angeles to San Francisco. I don't know if any of you are old enough to have seen a postal tube, but in the old days, we used to have vacuum tubes. You could connect an office with vacuum tubes, and you could put your mail in a little cartridge and stick it in the tube, and a vacuum would suck it down the tube and take it to the other building. And they don't exist anymore, but they used to be fairly common. In fact, Paris used to have a whole network of postal tubes. There was actually a central dispatch, and there were a network of postal tubes running from all the different business offices in downtown Paris up until the 1970s. But that's the idea of the postal tube. So let's take a look here at some of the characteristics of Hyperloop. So we have a vehicle. We have a vehicle that, according to them, is going to hold 28 passengers. And we want to carry a flow of passengers from Los Angeles to San Francisco, and perhaps the other way as well, assuming they want to come back. But we'll have a two-tube network here. That says we're going to go every 2 minutes. We're going to travel every 2 minutes on this tube. So that is a rate of flow of 30 per hour. We're going to have a rate of flow of 30 per hour. And rate of flow, and the time it's going to take, if you flip to Wikipedia, you'll see that the estimated journey time is 35 minutes. 35 minutes. I want to convert this to per minute. So that's 30 per hour. So that's one. So that's per minute. That's 1/2 per minute. So now my inventory on this system in one direction is 1/2 times 35, or 17.5 units. So we have to have 17 of these tubey, cartridgey things, these Hyperloop carriages, in the tube at once, 17.5 of them, traveling, roughly 2,000 kilometers an hour, just for benchmark figures here, but the speed of sound. And what do you got to do if you got to jump off? So we have 17, 18 of these things in the tube at any one time. They're traveling easily at 1,000 kilometers an hour, easily. And how much rate of flow are we getting, by the way? Let's figure this out. So every 2 minutes, 30 an hour, so 28 passengers times 30. So we're getting 286 and 840 passengers an hour. How many passengers in a 747 or Airbus 3 something? 300 passengers in an Airbus, give or take. So we're looking at 3 Airbuses. 3 Airbuses an hour. How many departures from Los Angeles to San Francisco in an hour do you think there are in the airports? Huh?
A lot.
A lot. Yeah, there's a lot. So this is the flow. This is supposed to approximate the flow of the existing air traffic between Los Angeles and San Francisco. So 840 passengers an hour. So we kind of got the flow idea in the rough benchmark here. So here's the deal. We got this guy and this guy. These are both tubies here with a load of smiling, happy passengers enjoying their drinks as they speed along here at 1,000 kilometers an hour. And 2 minutes between departures. What do we call this in railway terms? Headway. This is the headway. This is the headway between the departures. At 1,000 kilometers an hour, how far apart are they at 2 minutes? They're 1,000 divided by 60, 100 divided by 6, 50 divided by 3, 50 over 3 times 2, so that's 100 over 3. So they're about 30 kilometers apart. How long do you think it takes to stop from 1,000 kilometers an hour?
What kind of brakes? It's pressure brakes.
I mean, even if you just, magically could stop, what kind of acceleration would you experience if you were trying to stop from 1,000 kilometers an hour? I mean, a huge amount of acceleration, right? Right? So this is the problem. This is the problem. So how do you keep these two vehicles separate from each other? How do you keep these two vehicles from touching each other? And how do you regulate their position in the pipe? Because they're only 2 minutes apart. They're 30 kilometers apart, but at 1,000 kilometers an hour, they're really close together. And you've got a string of these. It's not just these two. It's continuous. In order to meet that statistic, there's no break. There's no gap. So this is a continuous flow. So realistically, that's not going to happen, right? Because you can't do it. You got to have some kind of break for mistakes, errors, robustness, blah, blah, blah. Here in railway stuff, we're talking 80%. Maybe we think we're really successful if we do 80% capacity infrastructure saturation. So you got to take 2 out of 10 of these out. So we're going to reduce our capacity right there. But from a safety point of view, this can't happen. Where's the signal system? Where's the driver? How do you stop one of these? They're in a tube with a vacuum air pressure sucking them along the pipe. There is no brake. There is no wheels. There is no switch. There is no siding. Nothing. So realistically, actually, that 2-minute headway is not going to happen. Because I can't imagine you loading up a cartridge full of 28 people and shooting it down this pipe before you got a signal from the other end saying the pipe was clear. So realistically, this is not a 2-minute headway. This is a 35-minute headway. Because you have to wait until the first cartridge has gotten to the end of the line before you give the all clear and send the next cartridge out down the pipe. And the only way you could avoid that is if you had brakes and physical machinery and all the things that they're trying to avoid by having this vacuum tube thing in the first place. So if you drop that down to a 35-minute headway, this all goes to pieces. 35-minute headway, so now our rate of flow is 60 over 35 per hour. And now our capacity then is 28. Maybe 60 passengers an hour, if you're lucky. So now suddenly this multi-billion-dollar thing is really actually not able to carry any more flow than a Greyhound bus on the highway. So this is where rocket science meets reality, right? And the ability to visualize how this is actually going to work in service and what kind of rolling stock, so to speak, that you need to support the service you're going to provide, and what kind of control systems you need to maintain safety in the vehicle, and how you're actually going to compensate for variation and robustness factors in the delivery of the service. These are all critical, and they don't go away just because you suddenly decided to put everybody in a giant vacuum tube. Yeah, Nava.
Yeah, this thing, it sounds like the neutron accelerator.
Yeah.
In the nuclear.
Yeah. It is. It's, we're just going to load everybody up. Yeah. It's, you know, but what's so frustrating is that this captured the fascination of the audience in California for a couple of news cycles, and it just took all the steam out of high-speed rail. Because suddenly everybody's like, oh, we don't need to build high-speed rail because they're going to build this postal tube next year. And politically, it's just hard to backpedal from that once that conversation starts. It's really hard to backpedal from that because you got a crowd who doesn't understand trains, and as we've just seen in the little piece of picture right here, I just finished looking at some kind of a Google image search picture of a fire crew that laid their fire hose across the railway tracks. And then they didn't want the train to cut their hose, so they put some little auto shop ramps over the hose to keep the train from cutting the hose. And so even though you got educated professionals, there's still a gap. There's a knowledge gap between those who kind of intuitively understand the technology of railways and those who don't. And that still is, even if you could be an educated public servant or, you know, policeman or fireman or something, and still not quite grasp all that reality. So anyway, all right, so